There is a train so fast that by the time you notice it, it's already gone. A few seconds is all you get. One moment, it's a shape on the horizon. The next, it's a blur. And then, nothing. Just wind and the strange feeling that you imagined. The whole thing. At full speed, this train crosses the ground at more than 600 kilometers per hour. That's faster than many commercial airplanes during the first moments after takeoff. And here's the part that breaks people's brains a little. Hundreds of tons of steel are moving at that speed, almost silently. No screaming engine, no wheels grinding against rails, just the sound of air being torn apart. So how does something that heavy move that fast? Without wheels, stick with me, because the answer takes us from a 200-year-old engineering problem through magnetic fields powerful enough to lift hundreds of tons off the ground, and all the way to an idea so extreme that engineers are now trying to remove the air itself. This is the story of how humans decided that friction, something we've relied on since the first wheel, had become the enemy. For more than 2 centuries, trains ran on a simple idea: steel wheels on steel rails. It's an elegant system. Steel on steel creates remarkably little friction compared to rubber tires on asphalt, which is why a train can haul thousands of tons of cargo across a continent using a fraction of the energy a fleet of trucks would need. For most of railway history, that low friction was the point. But advantages have a habit of turning into limits once pushed far enough. As trains got faster, the steel wheels began to vibrate, pressing down on the rails with enormous force. Any tiny imperfection in the track, a deviation of just a few millimeters, turned into a violent jolt at speed. The faster the train went, the more heat built up from friction, until the metal itself was under punishing stress. Engineers had to inspect, grind, and replace rail sections constantly, chasing near-obsessive precision. But the real limit was something called hunting oscillation. At extremely high speeds, a wheel doesn't just roll cleanly along a rail. It starts to sway, side to side, again and again, faster and faster, as if trying to escape the track altogether. The quicker the train goes, the worse this wobble becomes, until the whole machine edges toward losing control. This is why traditional wheeled trains hit a wall somewhere near 600 kilometers per hour. It was never really about the engine. being too weak. It was about contact itself. The moment metal touches metal, you inherit friction, vibration, and wear. A package deal that no amount of horsepower can escape. So, somewhere along the way, engineers asked a question that must have sounded almost absurd at the time. What if we just took the wheels off? If a train never touches the rail, friction very nearly disappears. And if friction disappears, speed can climb to places it's never reached before. That's the moment magnetic levitation, Maglev, stopped being science fiction and became an engineering discipline. Instead of rolling, the train is lifted, suspended above the track by an intensely powerful magnetic field, hovering just centimeters above the rail, held there with precision, measured in millimeters. Think about what that means. A machine weighing hundreds of tons, floating, not flying like a plane, with wings cutting through air, but hovering, low and steady, propelled forward by invisible force alone. To hold that gap steady, Maglev systems rely on electromagnets, whose pull and push can be adjusted instantly just by changing the electrical current running through them. That controllability is the whole trick. It's what lets engineers keep a several hundred-ton train balanced in midair, correcting itself thousands of times every second. There are two major approaches. EMS, electromagnetic suspension, pulls the train upward from below, attracted toward the track with extraordinary precision. EDS, electrodynamic suspension, pushes the train upward instead, creating a more stable lift once it's already moving fast. And here's a detail that tends to surprise people. A maglev train is actually more stable at extremely high speed than it is crawling along slowly. The faster it goes, the stronger and more precise the magnetic forces holding it steady become. Speed, in this case, isn't the enemy of stability. It's the ally. But lifting a train off the ground only solves half the problem. Once it's floating, something still has to push it forward. Here's the strangest fact about maglev trains. In the traditional sense, they don't really have an engine at all. No spinning wheels, no transmission, no pistons pounding away. And yet, the train accelerates to speeds that would shame most sports cars. The secret isn't inside the train. It's underneath it, stretched out across hundreds of kilometers of track. The technology is called a linear motor. Picture a normal electric motor, the kind that spins a shaft round and round. Now imagine unrolling that spinning motion into a straight line, stretching it out flat across the ground. For the length of the entire journey, That's essentially what a maglev track is. An electric motor that's been unwound and laid flat. Instead of turning wheels, magnetic coils embedded in the track switch, on and off, in a precisely timed sequence exactly matched to the train's position. This creates a traveling wave of magnetic force just ahead of the train, continuously pulling it forward, because there's no wheel friction eating away at the energy. Almost everything the system produces goes directly into acceleration. It's elegant but costly. The faster the train goes, the more electricity the system demands. And at peak speed, a single maglev train can draw as much power as a small neighborhood. Managing that in real time requires the track to function like a giant, continuously computing electronic brain, activating the right magnets at the right instant. In other words, a maglev train isn't just a vehicle. It's a floating computer system operating at the edge of what physics will allow. Removing wheel friction solves one enemy. It doesn't solve the other one, air. At over 600 kilometers per hour, the air in front of a train stops behaving like something soft and yielding. It starts to feel almost solid. A wall the train has to punch through again and again, every second of the journey. This is why high-speed train noses are so dramatically elongated, shaped almost like a jet's fuselage. That shape lets air slide smoothly around the train instead of slamming into it, cutting down on pressure buildup and dangerous vibration. Engineers have tested hundreds of nose cone designs just to shave off a few percentage points of drag. Some of the best breakthroughs came from nature. Japanese engineers famously studied the kingfisher, a bird that dives into water at speed with barely a splash. That same principle, a long tapering profile that displaces air rather than fighting it, helped solve one of Maglev's nastiest problems: the shock wave-like pressure spike when a train enters a tunnel at full speed. At these velocities, air, quite literally, starts behaving less like a gas and more like a resistant, almost solid medium. And here's a fact that catches people off guard. Most of the energy a high-speed train consumes isn't spent overcoming friction. It's spent fighting the air. This is exactly the pressure point that pushed engineers toward an idea that sounds almost reckless. What if you could remove most of the air too? Before we get to that idea, it's worth pausing on just how demanding it is to keep a maglev train stable in the first place. At 600+ kilometers per hour, The hardest problem isn't acceleration. It's staying steady, a deviation of just a few millimeters in the track can force the control system to react in a fraction of a second. Sensors on board are constantly measuring distance, vibration, speed, and magnetic field strength thousands of times every second, feeding that data to a central computer that adjusts the magnetic force in real time. The train, in a very real sense, is continuously balancing itself thousands of times per second for the entire duration of the trip. If the response lags by even a few milliseconds, forces can spike beyond safe limits almost instantly. Humans simply can't react at that speed, which is exactly why automation and artificial intelligence have become essential components of modern high-speed rail. It isn't only an electronics problem either. It's a materials science problem too. As the train accelerates, its structure expands, vibrates, and absorbs continuous stress from its environment. Engineers rely on materials that are extraordinarily light yet extremely rigid, trying to minimize vibration without compromising safety. Even ambient temperature can affect how much the rail and the levitation system expand or contract. At extreme speed, the strange payoff of all this obsessive engineering? When everything works as intended, passengers inside often barely sense the speed at all. That's the real triumph hiding underneath the headline. Number turning something violent and physics-defying into a ride that feels almost like floating in still air. Even with all of that mastered, engineers still haven't stopped chasing more speed. And that ambition leads somewhere even stranger: Hyperloop. The idea is almost brutally simple. If most of a train's drag comes from punching through air, then remove the air. Hyperloop systems are designed to run inside tubes that are nearly vacuum. Pressure reduced so dramatically that air resistance essentially disappears. Once you take air resistance out of the equation, speed climbs to numbers that sound almost implausible for something running along the ground. Some Hyperloop concepts target speeds beyond 1,000 kilometers per hour, faster than most high-speed rail in operation today, and closing in on the cruising speed of commercial jets. If that ever becomes reality at scale, travel between major cities could shrink from hours to a matter of minutes. Of course, maintaining a near-vacuum environment across hundreds of kilometers of tube is an engineering nightmare. Even a small leak can shift internal pressure enough to threaten the entire system. Add in thermal expansion, vibration, and structural stress at extreme velocity, and you start to understand why Hyperloop is considered one of the hardest transportation problems modern engineering has ever attempted. Some experts believe it could reshape how cities and economies are structured. Others argue the cost and complexity will keep it from ever becoming widespread. So, let's zoom out for a second. Because this isn't really just a story about trains. If ground transportation genuinely closes the gap with air travel, the way humans live could change in ways that ripple far beyond the railway. Cities hundreds of kilometers apart could functionally become commuting distance, somewhere you traveled to for work and return from the same evening. That's not just a transportation shift. That's a shift in economics, real estate, and how entire regions connect to one another. High-speed rail has a genuine structural advantage. Here, no security lines built around distant terminals, no long drive just to reach the starting point, a train that departs from the middle of a city can beat a plane on total door-to-door time, even when its top speed is lower. Building that kind of network at global scale demands infrastructure investment on a scale most countries have never attempted. Enormous, continuous power supplies, near-perfect track precision, and control systems that leave almost no room for error. It's part of why only a small handful of nations have the resources and expertise to build high-speed rail at real scale today. Strip away the magnets, the linear motors, the vacuum tubes, and what you're left with is a surprisingly simple idea. Remove friction and see how far you can go. From steel wheels grinding against steel rails to trains that float above the ground. Entirely, human transportation has evolved faster in the last few decades than in the previous century combined. Trains crossing the ground at over 600 kilometers per hour were considered close to impossible only a few decades ago. Maybe someday we'll look back at today's fastest trains the way we now look back at steam locomotives. Quaint, almost primitive. A stepping stone towards something we can barely imagine yet. Because the real limit on technology has rarely been physics itself. It's been how far humans were willing to imagine in the first place. And if history is any guide, we're not done pushing. The gap between countries, between cities, between people, measured today in hours, might one day be measured in minutes. Whether that future arrives through magnetism, near vacuum tubes, or something nobody's thought of yet, one thing about human nature hasn't changed. Since the first wheel ever turned, we have never once been satisfied with how fast we can already go.